Guys, welcome back. And what you're seeing on the screen is another chirality problem. Aren't you happy? So up here at the top it says, which is R and which is S? Or are they the same? Oh gosh, now they're trying to trick me even more. Right? In the previous questions, they were like, identify the chiral carbons, and that was it. And then later on, they were like, hey, keep in mind that you might not have a chiral carbon. Okay, well, there was another trick. And then after that, they were like, okay, draw the R and S forms if it does have a chiral carbon. So we got comfortable with that maybe. And now they're giving me structures and they're saying, label them as R, label them as S, but keep in mind we could give you the same thing. Ha 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 ha. That's the trick that they like to do with you. So don't let them trick you. These things are very easy as long as they're drawn in the proper format. So that's the caveat though, that's the trick, and that will be a trick much later on. So here in this example problem, I see hydrogen which is on the back end. So therefore this does set up the proper orientation for me. I need to look at these three groups that they've given me, bromine, ethyl, methyl. We've seen this before, right? They like to use this example, so whatever. So here is the highest rank number because it has the highest atomic number. And then the ethyl group has 2 carbons. It beats out the methyl group with 3, or with 1 carbon. So that's my third group. So rank 1, rank 2, rank 3. That's the rotation. It's counterclockwise. It starts up at the top and it points to my left hand. So therefore, this is the S form of 2-bromobutane. So if you want to know what these things look like as far as names go, we normally put that in parentheses, and then we write out the IUPAC name just like normal. I mean, there's no difference here on this end. So cis and trans went into the front. They didn't have parentheses on them, but E and Z went into the front, and we did put parentheses around E and Z. And we'll do the same thing here. R and S goes in front, and R and S goes into parentheses. Okay? Also, at the same time, I do want you to understand that you can have more than one chiral. And if that's the case, then sometimes you might have like an R and an R, or you might have an S and an S, or you might have like an R and an S, or you could have an S and an R, or you could have like an R and an S and another R if there's 3 chiral carbons. That is how we would represent them in the front. Okay, so we would separate them with commas, but we would include the entire thing in parentheses. In addition to that, if there is more than 1 chiral carbon, then that chirality needs to be assigned the number that's on that carbon. So for instance, if this is the 2nd carbon in and this is the 5th carbon in, or if this is the 3rd carbon in and this is the 5th carbon in. I mean, I don't know. I'm just making those numbers up. But that's how we would represent that. So we would know on that 3rd carbon, we have the S configuration. On the 5th carbon, we also have the S configuration. That's how we would interpret that in a name if it's given to me in IUPAC. All right. Same thing up here at the top. We'll separate these by commas, and this could have a 2, and maybe this could have a 5, and this could have like a 9. I don't know. I'm just putting numbers on there. So 3 chiral carbons. Those are the locations of the chiral carbons, and that is the rotation around the molecule in that chiral carbon. Now, we've not answered the question. I went off on a tangent, but that was a good time to introduce that. So over on the right-hand side, we need to figure out, is that R or is that S? Did they give me the same thing and just draw it a different way? So lower priority group is in the back, which is good. That's what it needs to be. Here is group number 1. There's group number 2. Here's group number 3. That's the rotation. Folks, that is a clockwise rotation. It goes to my right hand. So this is the R form of 2-bromobutane. All right? Okay, so if you feel good about that, that's great, but I'm getting ready to switch some things on you now, and you're probably going to drive you crazy. All right, so what's up next? Something very similar, but remember I told you about mean biologists, mean and nasty, mean biologists that come into the play and say, ew, I don't like the R and the S. I want to do something that I want to do. Okay, well, fine. Have at it. Go play. But because of that, there is another system at play. And we've got to figure out how we interpret that system as well as the R and S system. So what is this new system going to be called? Well, we've already mentioned it. This is going to be called the Fischer projection, right? What we've been doing have been perspective formulas. These were perspective because it gave you perspective of the 3D. It gave you the solid wedge and it gave you the dashed wedge. But Fischer projections are also part of this conversation. And this is for people who don't want to draw the solid and the dashed wedge. It's for people that want to know R and S, because that's what we gather from this. We can determine if something is R or S based on a Fischer projection. But it's just drawn a different way. And I think the trickiest thing here is to realize what bonds represent what. In other words, what represents the solid wedges and what represents the dashed wedges. So here is my simplified version on Fischer projections for you. When we draw, so that's going to be the first step. We're going to draw it in the Fischer projection template. That looks a little different than what we've been doing before. When we do that, we are then going to rank those groups. And we're going to rank them just as we did before. There's no changes. You rank them just like you do with perspective. Okay? When you rank them, step 3, look at your lowest priority group. In perspective formulas, if we had a hydrogen, that would be the lowest by default. And that would always be pointed back, right? That would be pointed away from us. So we had a certain template that we needed that R and S to match. And if it didn't match that, then, we had to maybe turn things around a little bit until it did. But lowest priority has to go in the back. So with the Fischer projection, we look for the lowest priority, but this is different because it doesn't use solid and dashed wedges. We look at the position of whether or not it is on a vertical bond or a horizontal bond. Vertical bond, of course, goes straight up and down. Okay? Horizontal is horizon. If you look out to the horizon, it goes left and right, like this. It's where the sea meets the sky. I feel like I need to be an inspirational writer. So in the Fischer projection, if the lowest priority is on a vertical bond, if it's on a vertical bond, and you rank the groups like you've done, everything is the same. That's good for us. That means if this rotation goes to my right hand or clockwise, this is R. And if the rotation goes to the left hand or counterclockwise, this is S. Just like before. No difference. No difference. But it's got to be on a vertical bond. A bond that either points straight up or a bond that points straight down. Thanks, biology. Keep that in mind. Actually, the real story is a little bit more complicated than that. But I've got to blame somebody, and that's a very easy target to blame. Now, with the horizontal, if the lowest priority group is on the horizontal bond, either pointed to the left or pointed to the right, it doesn't matter which, you're still going to rank them, you're still going to draw the arrows. Okay? So if the arrows go to my right hand, or if the arrows go to my left hand, we still look at that. If they go to the right hand, we normally pick R. If they go to the left hand, we normally pick S. But if it's on horizontal, that means it's on backward. So the easiest thing for me to tell you to do here, look at your Fischer projections. Find your lowest priority group. If it's up and down, then there's no changes. You do what you've always done. Call it a day. If it's horizontal, though, do what you've always done. Look at your ranking. Draw your arrow. Look at clockwise. Look at counterclockwise. And when you determine what it would normally be, just pick the other answer because it's backward. So if it normally went clockwise, we normally would give it R. But if that lowest priority group is horizontal, we're going to change our answer and we're going to put an S here. And then if it goes left-handed, we're going to put an R there because, once again, horizontal means backward. The biggest key here, no rotate. The way that you draw them on that sheet of paper is the way they have to be stuck. You're not going to kind of imagine these turning around and twisting and doing things on you. Not going to do it. Not going to do it. Not going to do it. Horizontal and vertical bonds mean something very specific. So the way that you put them on a sheet of paper, they're stuck, folks. They're pretty much stuck. So let me give you an example of what we're talking about. And again, you might like these a little bit better. Who knows? I don't know. So with Fischer projections, how do we draw the structure? Like this. We make a cross. There's two vertical bonds, up, down, and there's two horizontal bonds, left, right. There you go. That's what we're referring to. This crisscross in the center, this is the chiral carbon. That's what we're so focused on. Notice they don't even draw a carbon there. They don't even draw what it's supposed to be. They just put a crosshair and say, you're supposed to know. All right, not a big deal. So let's say that we have a chlorine here, maybe a propyl group here, CH2, CH2, CH3. Down here, a hydrogen. And here we'll do an ethyl group, CH2, CH3. And this question is going to say, okay, use the drawing that we've just provided you. This is a Fischer projection, by the way. I know it's Fischer because there's no solid or dashed wedge. And rank it as an R or an S. Okay, so this is how we do it. Number one, find the lowest priority group. My lowest priority group is the hydrogen. It has the lowest atomic number, so there's the lowest. And this is on a vertical bond, isn't it? Yes, it is. It's pointed down, but it's a vertical bond. It's either going straight up or straight down, and that's where it needs to be. So from this point, everything else goes normal. I find my highest group. My highest group is going to be chlorine, highest atomic number. Carbon, carbon is a tie. What's next? Carbon, carbon, that's a tie. What's next? Carbon, and that runs out. So this is rank 2, and this is rank 3. Just like with perspective, I say, hey, higher one up here. I point it to my next in line, which is there. Then I point it to the next in line, which is there. And that is a clockwise rotation. That points to my right hand. So therefore, this is the R form of that molecule. And you are just now giving me a correct answer. That's how we do Fischer projections, folks. That's it. Okay, so what if I wanted to represent the S? Well, this is how easy this is. You do your crisscross, the chlorine stays, the hydrogen stays. Do the mirror image, flip it around. So we'll do CH2, CH2, CH3 here, and we'll do CH2 and CH3 there. Well, lower priorities at the bottom. It's a vertical bond. Therefore, I can rank these just like before. Rank 1, rank 2, rank 3. Here's the arrow that goes around. That is counterclockwise. Counterclockwise, or the arrow points to my left hand. This is the S form. Everything goes as planned, as long as that low group number is on a vertical bond. It could have been pointed up. It could have been at that chlorine. No big deal. it still would have been on a vertical bond, and we still would have been issuing it as an R or an S. Our answers would not change anything. Okay? Now, let's do another example. Let's take a look at another Fischer projection. Let's put an OH group here, a hydrogen here, a CH2, CH3 group there, and a CH3 group here. Rank it as R or rank it as S. Fischer projection at play. Okay, so I find my lowest group number. Right there, right here, right there it is. But uh-oh, we're on a horizontal bond. We're not vertical. So here's how I'm telling you to fix it. It's a very easy fix. Ignore it for now. Ignore it. There is the lowest group number. Just hide it away. Sweep it under the rug. Come back to it a little bit later when company leaves. I've got 3 groups that are left. What is my high priority group? I hope you're going to tell me OH because that has the highest atomic number, O, versus the 2 carbons. And then out of these 2, which one's next? I hope you're going to tell me ethyl group because that has 2 of them and this one runs out, so that will be number 3. Draw your circle. Draw the arrows. How does it rotate? Well, here's spot number 1, then it goes to spot number 2, and then it goes to spot number 3. Folks, that's clockwise, isn't it? Yes, that's clockwise. So what that means is that under normal circumstances, this would be the R form, because it's clockwise. Okay, but, here's the but. Hydrogen is on a horizontal bond, which means that in a perspective formula, it's not really pointed away from you, it's pointed towards you. That is not the proper orientation for these. So if hydrogen is on a bond to the left or to the right in a Fischer projection, you just told me what this answer would be normally, you pick the other one. So this is going to be an S. My hydrogen is backward. My hydrogen's not where it needs to be. It's in the opposite location. So we pick the opposite rotation. So it's not an R, but it's an S because of that reason. All right, so let me do it again. Using the same groups, let me put my hydrogen here, and let's put the OH group here, and then let's put my CH3, CH2 group here, and let's put my methyl group here. What is that one? Is it the same? Is it different? What is it? Well, let's find out. Lower priority group hydrogen here. I don't rank it. I leave it alone. Forget about it. Look at your other groups. Rank 1, rank 2, rank 3. So here is a counterclockwise rotation, right? It's counterclockwise. So normally, this counterclockwise rotation would mean a S has been involved. But then I go back and I double check my low priority group. And I have to remember this low priority group was on a horizontal bond. It went either left or right. It's in the opposite location of where it needs to be. So therefore, I need to pick the opposite rotation of what it needs to be. So because hydrogen is on a horizontal bond, this is not an S, but this represents a R instead. So they are different. Those 2 examples are different rotations. So folks, what you see in this example, maybe a little bit clearly drawn out for you and not my chicken scratch handwriting, but these are just 2 examples of Fischer projections, and they've named them lactic acid. So lactic acid, very similar to lactose. Lactose, you might think of milk. So this is more of a biological kind of perspective, and again, that's where this Fischer projection really plays a heavy foot. So here's lactic acid to the left and lactic acid to the right, right? It's the same number of carbons, same number of hydrogens, same number of oxygens. It is attached in the same exact way, so therefore they both are lactic acid. The only difference is that there's a chiral carbon in the center, and that's where it's located, and that chiral carbon points the groups in different directions. That's the only difference between these 2 molecules. So we have an R and we have an S form. Here we see hydrogen on a horizontal bond, okay? So here's group number 1, which is my OH group. Group number 2 is this carbonyl group, or really carboxylic acid group. That's number 2. And then my methyl is group number 3. How do I know that? O beats them out in atomic number. Carbon's tied. Then we go on to the next, and that's an oxygen, and this runs out. So this by default beats methyl group. Well, normally this is rotating spot number 1, spot number 2, spot number 2, spot number 3. That is a clockwise rotation. So normally we would assign this as R. However, hydrogen's on a horizontal bond. It's the opposite of where it needs to be. So we choose an S instead. Over here to the right-hand side, same description. Okay? My OH is group number 1. My carboxylic acid is still group 2. My methyl group is still group 3. Group number 1 goes to group number 2. Group number 2 goes to group number 3. That is counterclockwise. That counterclockwise rotation means normally this would be an S. However, in this case, hydrogen is on a horizontal bond. I have to pick the opposite of. So it's not S, but it's R. And that is how they get the R and S designations for those Fischer projections where hydrogen is not at the top nor at the bottom. Okay? All right, so that's where this video is going to stop. I've introduced you to R and S. I've introduced you now to Fischer projection. And I need to introduce you to another concept that plays a role in stereochemistry. And that's this thing called optical activity. So come back to me. We're going to sit down. We're going to have a nice fire chat about optical activity. You know, bring some marshmallows, bring some s'mores. We'll sit down on the rug, talk about the good old times when Jean-Baptiste Biot was around. And that was about the late 1700s. So hope you're up for a history lesson. That's what you're going to get when you come back.